Hey, welcome back to Math with Patrick and Quill. Today is October 11th, and we're solving problem 284 from the Daily Epsilon calendar. And we need to find the largest root of this polynomial. Looks like it's a cubic polynomial. We have a lot of ones for our coefficients, and supposedly the largest root of this polynomial is positive 11. So let's seek out these roots. I think I'm going to use the rational root theorem. This is just a way to create a list of potential roots of your polynomial. And vocab word, a root is just a number that I could plug in for x here to get this to be equal to 0. So the rational root theorem states that if we happen to have rational roots, that is like a fractional number that makes us equal 0, or like an integer, like a whole number that makes us equal 0. If we have rational roots, they're going to be of a certain type. Essentially, we're going to have factors of this number on top and factors of that number on bottom of our rational root. And these could be either positive or negative. So factors of 11 are just 1 and 11, and then factors of 11 are just 1 and 11. And I could kind of pick and choose which numbers I want here, because either way, or actually not either way, but any way I pick a top number and a bottom number, these are all potential rational roots for my polynomial. So I could do positive or negative 1 over 1, positive or negative 1 over 11, positive or negative 11 over 1, and then finally positive or negative 11 over 11. And you'll notice that this number and this number happen to coincide. This happens occasionally when you do the rational root theorem. I think maybe actually every time. I don't know. Let's just say at least sometimes. So our potential roots are going to be positive and negative 1, positive and negative 11, and then I'll put the positive or negative 1 over 11 here just to kind of have it in order from least absolute value to greatest. So maybe our roots are going to be one of these 6, and again, none of them might also be roots, because it's totally possible that our polynomial doesn't have rational roots, but rather irrational roots. Although I'm hoping that since it's a problem in a fun math calendar, we are going to get some rational roots for today. And I know that 11 is right here, but I'm pretending that I don't know that yet. The first thing that I do is actually I'd probably check this 1 or negative 1. That just seems easiest for me. And I'm going to use a strategy called synthetic division to just check if 1 or negative 1 is going to be one of my roots. So this 1 or this negative 1 is the root, and then I will line up the coefficients of my polynomial kind of like that. And the process here, basically it mimics long division, and I'm just going to drop this number down, multiply it by the 1, and then put that there, and then add these. So I get negative 100, multiply these, add these, negative 211, multiply these, and then finally add these. And if this number were a 0, that would suggest that like my remainder after division would be 0, and therefore that I found a factor of my original polynomial. But because the remainder is not 0, then it doesn't divide it evenly. So onwards to checking other roots. Okay, drop the 11 down, multiply by the negative 1, add these together, that's negative 122. Multiply those, we're going to get a positive 122. Add these, that's positive 11. Multiply these, that's negative 11. And what do you know? We actually do get a 0 here. So this shows me that the corresponding factor of the root of negative 1 is going to be x plus 1. And this is a factor of my original polynomial. So I'm going to get x plus 1 times, and then some kind of quadratic, because this would have like degree 2. This is degree 1, and then multiplying these together would give me a cubic back. And fortunately, the synthetic division also just tells me the coefficients of my quadratic polynomial. It's going to be 11 squared minus 122 plus 11. And, well, I did find -1 is a root. And so currently, that is my best guess for today's date. Today is October -1st, and unless I find a larger root, then the answer is -1. Of course, it's 11. So let's try factoring this quadratic here. I'm thinking, and I'm hoping, that it's just kind of factorable with whole numbers. And so knowing that this is a minus sign and that is a plus sign, it looks like I need minuses in both of my factors. And then these are both 11s. So I either have like x, x, and then 11, 1. Oh, wait, hold on. 11 and 1. And then I guess to make this 11, is it like this? Maybe? Because redistributing everything, we get 11x squared minus x minus 121x and then plus 11. Oh, cool. All right. I just kind of stumbled upon the right factoring of this. Wasn't too hard given like the kind of features of the positive and the negative signs and the fact that my a and c values were both prime. But anyhow, I have now completely factored my polynomial, and this shows that I have roots of -1, of 11, and then finally of 1/11th. And between these three roots, 11 is the greatest. So that's my solution, just basically factoring and then finding roots with that. Today's date is the 11th, and so it's good that 11 is the answer. And I also could have solved this problem by just graphing it and just finding this x-intercept at like 11, 0. That would have been probably the easiest solution, but I figured why not? I'll show it more algebraically than graphically. So thanks for watching. We're all done, and I'll see you tomorrow. Bye.